Hello guys and welcome. Today I want to talk about quantum computers and how they can be practically applied to solve our most everyday problems. Especially I will talk about the latest developments and the latest machines that were built by now. On top of that, I will talk how they can be applied in the fields of biology and medicine, in the fields of logistics, in the field of cryptology and protecting our data, as well as in fields of finance, which will go from banks to optimizing the work of stock market and stock exchange. It is a really large topic and I will especially develop on it.
First of all, let's briefly go over what quantum computers are. The basis of it lies in a completely new approach to the computing. Instead of relying on the classical bits that are either 1 or 0, the qubits combine both in themselves. This allows them to exist in multiple states at once, enabling them to conduct a large multitude of computations at the same time. This is comparable to a Schrodinger's cat that can exist in two states at once. Qubits can be made of anything that exhibits quantum behavior, molecules, atoms, electrons, etc. They would be even more accurate than the classical sodium-based computers that have 70 to 200% error chance in their computations due to it. Not to mention that the more electrons in a molecule are used for such purpose, the more possible states for it there will be. For example, a molecule with 10 electrons will have 1000 possible states, while a molecule with 20 electrons will have over 1 million of possible states. There is also quantum entanglement that must be mentioned. It interlinks all of the qubits, allowing them to operate together. Together with superposition, it allows quantum computers to process large quantities of information in far greater amounts than what classical computers can process. Quantum computers can calculate infinite possibilities for their inputs. They can model more complex algorithms and develop far more intricate and sophisticated models. The most practical application of it would be processing vast amounts of market data of the stock exchange, modeling molecules with all of their details and intricacies for pharmacological purposes, and calculating the most optimal logistical routes, and those are just to name a few. There are two most common types of quantum computers. First is based on the quantum gate model and quantum circuits. In a way, it resembles the current classical computers. IBM Q System 1 would be the perfect example of such. It is the first full-fledged, commercially available quantum computer that was introduced earlier this year. Second type are the superconducting quantum computers. The largest ones have over 2000 qubits and are produced by D-Wave systems. Those rely on quantum annealing, which is global minimum of a given function, over a given set of candidate solutions. To get a better practical understanding on how those computers will work on practice, let's take a look at IBM Q. There are two main conditions that have to be met in order for the quantum computer to work. First is achieving near absolute zero temperature, which is around minus 237 degrees Celsius. Second is the absolute vacuum. Those are no easy to achieve and maintain, but they have been attained in IBM Q System 1 and its previous iteration. On top of that, there is a good reason for the entire computer to be encased in a protective metal cylinder and placed in a hardened glass box. Quantum chips are extremely fragile, and even the slightest interference will be damaging for them. The prototype has managed to get 20 qubits working and operational. It has also doubled its QV network volume from 8 to 16 in comparison to the last iteration. Such computing power opens a great potential for the practical applications. In addition to considerable computing power, it has the lowest error rates, which are around 1 or 2%. That are some of the lowest what IBM has ever measured. This is the quantum-ready computer, meaning that it's on par with the current classical ones. The future plans involve creating a computer with a quantum supremacy, or a quantum-ready computer in IBM's terms. It will have a greater computing power than the classical computers. This should be achieved in around 3 to 5 years, if everything goes to schedule. The most advanced quantum computer is the one used by Google. It has 72 qubits, and Google has already claimed that it has reached quantum superiority not so long ago, which is a considerable milestone in quantum computing. Another interesting device is being developed by the Rigetti Computing. They aim to build a 128-qubit computer that will be unveiled this year. It is developed on their new form factor that lends itself to rapid scaling. Because of their in-house design, with all of the teams working close together, they should be able to develop and deploy new systems really quickly. Also, quantum computers are a new valid application of Moore's law and should double the computer transistor's performance every year. This should culminate in one of the goals of quantum computing, creating a big enough quantum computer that will be infinitely more powerful than any classical computer that has ever existed. The first extremely practical application that would affect a lot of people would be the simulations of the biological molecules. This would allow a significantly improve drug design and better determine positive treatment effects as well as negative side effects. Another probable application would be the quantum applications for the internet. First of all, it will involve encoding a qubit with far more information than a conventional bit can handle. Second, it will improve the security of transmitted messages. On top of quantum encoding, it will be also possible to detect any attempts to intercept messages due to the nature of qubits that react when they were influenced by any third-party intruder, such as malicious hacker or something like that. It will be possible to switch to the quantum internet once the existing broadband technologies are improved. Photons can be used as qubits, which makes fiber optic cables applicable for such purposes. Moreover, a recent breakthrough by Australian scientists can make erbium the prime substance for enabling it in existing networks. They have found that applying a large magnetic field can greatly improve the quantum storage time for certain erbium crystals. This field, which is similar to that inside a hospital MRI machine, quiets the magnetic field fluctuations. The erbium time can then improve by a factor of 1,000 to more than 1 second. The most fascinating applications of quantum computers are in the fields of finance, and probably the most complex ones. The entire financial market can be modeled as a quantum process, where quantities that are usable for quantum computing, such as covariance metrics, emerge naturally. In addition to that, some well-known financial problems can be directly expressed in quantum mechanical form. There was a scientific paper that dwelled deeply into research on this subject, of applying quantum algorithm to solve the existing financial tasks. Not to mention that having such operating quantum computer with large enough capacity would provide a significant advantage to the ones who would actually own it. First of all, a large number of problems in finance have to do with optimization. Those can be addressed with quantum annealers that were mentioned earlier. A valid application would be searching for patterns in the past data in order to predict future market patterns and fluctuations, which is the core of any modern-day technical analysis. It can be greatly enhanced with the improved machine learning speeds that quantum computers provide, which would be both faster and more affordable than existing methods, allowing them to go through larger data quantities that classical computers are capable of and that they can handle, and even more so with an annual increase in the number of qubits that we should expect. Finance also deals with uncertainty of future behavior of assets and their projected returns. Risk in financial terms is the possibility of difference between actual and expected return. This risk can be purposely mitigated, particularly in case of high return risky assets, by selecting additional assets and creating a more stable portfolio. Both portfolios and assets are intrinsically random systems due to inherently incomplete knowledge of the market. This randomness is a risk that is very difficult to estimate. However, numerical simulation, such as Monte Carlo 1, can be used to estimate what an option is worth, and quantum computers can be applied to solve related computational issues in such calculations. In this case, portfolio optimization can be done using a model that is trained to identify the important data. Then it can be used to predict the behavior of new data points, which is basically the process of machine learning. The particular improvements that quantum computers provide would be in speeding up the training of such a model. Monte Carlo methods, statistical sampling, can usually be implemented efficiently. They would, however, require more runs to provide an accurate estimation of the expected return and its distribution. Its accuracy can be further improved by modeling the parameters as stochastic functions, yet there is a colossal computational power required to accurately describe the system. This only gets higher as the amount of data gathered increases, which is an issue that quantum computers are best suited to solve. And the faster the required algorithms can run, the greater the advantage it will provide. Grover's algorithm is another important application of quantum algorithms. Its function is finding a particular register in unordered database at a significantly greater efficiency than typical algorithms. It can be adapted to solve optimization problems, help to find flow-like variables, and implement Monte Carlo methods. The above dynamic portfolio optimization was successfully done on D-Wave chips, proving that it can be solved with high success rate on quantum computers. In the previously mentioned research paper, there are other formulas that demonstrate the exact working of the quantum algorithms listed in this video. If one desires to get a deeper understanding of its workings, I would highly advise the reader to follow the link below to the research document. Let's take another financial practice that can be better solved using quantum algorithms. Arbitrage, the practice of making a profit from differing prices on the same asset in different markets. The problems of this subject are NP-hard, non-deterministic polynomial time hardness, which makes them perfect for quantum algorithms to handle, particularly for quantum annealers. Moreover, the practical instances of arbitrage problems that were converted into quadratic unconstrained binary optimization, or QUBO, that when implemented on D-Wave quantum annealers have produced the same optimal solutions as an exhaustive classical solver. Another important financial issue that quantum computers can successfully tackle is credit scoring, being the basis of determining the risk of a loan and the likelihood of the borrower defaulting on payments. It can be translated to QUBO problem as well, that can be run on quantum annealer. Apart from that, the problems that arise from lack of data or from having to deal with large quantities of data are a prime subject of quantum computers to deal with. In this case, it was implemented as proof principle in 1-qubit SDK toolkit, and the results have shown that future quantum annealers can be used to find optimal features in credit analysis. It is also important to elaborate on the prospects of machine learning with quantum computers. As was previously mentioned, the entire process can be made more efficient and less time-consuming. On top of that, the produced algorithms can tackle a large diversity of tasks. Those would include pattern recognition, data classification, and many more. The training of AI to perform those tasks can be significantly improved. Let's take a look at classification algorithms. In our example, each data point, which is a customer, can be expressed as a vector, with vector space of all considered attributes. Each vector in turn would belong to a class. A certain loan risk, such as classification algorithm, would be an essential tool for financial predictions. And the methods for running the classification algorithms on a quantum computer would be generally focused on efficiently performing projection operations. Imur, Brassard, and Gams were pioneers of the idea of recasting the above problem in a quantum computer by expressing each data point as a quantum state. They developed the idea of Burman to efficiently estimate the classical distance between states by repeatedly performing swap tests. Lloyd also suggested an alternative method for encoding classical data in a quantum state, while also relying on swap tests. It boasts efficiency that is greater than classical algorithms. There are also early suggestions for the application of quantum classification algorithms to pattern recognition problems. Financial supply chain management is an important subject as well. It has to do with meeting customer demand while avoiding unwanted stock. Same as classification algorithms, it requires taking a significant number of factors into account that relate to every specific problem. It requires to learn a numeric function from the training dataset and employs regression, core tool for economic forecasting. It is used to gain an understanding of how the typical value of a response variable changes as an attribute is varied. The optimal parameters are found by minimizing the least squares error between the training data and the values predicted by the model. Done by defining pseudo-inverse of the training data matrix, this can be computationally expensive for classical datasets, but not for the quantum ones. Also, Wiebe, Brown, and Lloyd managed to apply a powerful mathematical toolbox to perform regression on quantum computer. In their example, a sparse training data matrix was used to encode the model's optimal fit parameters into the amplitudes of quantum state, which is far faster than the fastest classical algorithm. Wang has managed to improve on it by applying the modern methods for matrix inversion and generalizing the algorithm to non-sparse training data matrices. Another method applicable to this kind of task was Gaussian process regression. The last development of the subject was done by Schul, Sinaisky, and Petruccione, who managed to solve the expensive data size problem by encoding the regression model into a quantum state. However, that solution is rather inconvenient at the current stage of this development. In terms of portfolio optimization, it is very important to have a global vision of interest rate paths, even when dealing with hundreds of swap instruments. A standard machine learning tool for this principle, component analysis, or PCA, it amounts to finding dominant eigenvalues and eigenvectors for a very large matrix. However, when the number of stocks reaches over millions, the cost becomes astronomical. The PCA algorithm can be run exponentially faster on a quantum processor. It allows us to find approximations to the principal components of a correlation matrix, as well as estimate risks and maximize profit in situations not feasible using classical methods. Neural networks have proved to be extremely successful at predicting markets and analyzing credit risk. The key to their success lies in the ability to tackle tasks that require intuitive judgment for incomplete datasets. This makes them essential for financial prediction. They too can be accelerated through quantum computing. Quantum annealers can significantly reduce the computational cost of machine learning. Moreover, once trained, the algorithm can be used on any classical computer. The previously mentioned PCA can be used to speed up the process exponentially, and fully new quantum neural network algorithms can be designed for that purpose, altogether allowing the network to learn much more complex data patterns. Coming back to Monte Carlo's methods, they perform best when dealing with extremely large or complex systems that can be handled otherwise, as the stochastic approach is usually used to simulate the effect of uncertainties affecting the given financial objects, which can be stocks, portfolios, or options, which makes Monte Carlo methods applicable to portfolio evaluation, personal finance planning, risk evaluation, and derivatives pricing. In order to obtain the most probable outcome of wide distribution, or to get results with a very small associated error, the necessary number of Monte Carlo simulations can become gigantic. For example, stock market simulations that are usually day-long simulations. A quantum speedup would bring a huge change, greatly speeding up the process. The first steps were done by Broussard, Hoyer, Mosse, and Tapp. In the first part documented in the research paper, they extend Grover's research algorithm to construct the quantum amplitude estimation (QAE) algorithm, which can be used to get the quadratic speedup in calculation of expectation values by Monte Carlo sampling. It applies a series of QAA operations, followed by QFT from Shor's quantum factoring algorithm, to measure the approximate amplitude of any given state. Developing from the obtained results, Montanaro showed that Monte Carlo simulations can run on a quantum computer with the same accuracy as classical machines, as with quadratically fewer samples required, QAE algorithm serving as source of a speedup. Additionally, if random sampling is performed through a quantum algorithm, this can provide another speed increase. Building up Montanaro's work, Robin Trost, Grout, and Bromley suggested using quantum-accelerated Monte Carlo to obtain quadratic speedup in pricing financial derivatives, while Warner and Egger pioneered the idea of adapting the core principles of such efficiently estimating VAR and CVAR for financial risk analysis. By applying QAE algorithms, they determined that VAR, which is value at risk, and CVAR, which is conditional value at risk, with a quadratic speedup as well, and it was actually tested by IBM Experience. Quantum computers already have several applications in the field of finance. Moreover, some of those applications were tested and yielded great results. That's considering the current initial stage of their development. Therefore, it can be concluded that the greater the increase of their computing power will be, the greater will be the speedups, and the more tasks they will be able to handle. It is quite certain that at one point they will become powerful enough to become disruptive in the field of finance, meaning that whoever would own a powerful quantum computing machine would have a tremendous advantage over others. It is important to note that the above are only a few of possible applications, and such fields as quantum teleportation have not even been mentioned. By now, it is evident that quantum computers are growing in their computing power at an increasing rate. The greatest example would be the machine that has already achieved quantum superiority, which is created and developed by Google. And the faster the development goes, the more institutions and companies will be drawn to quantum computing, which will bring a greater development speed, with everyone contributing their part to their grandiose technological development.
Thank you for watching the video. If you really enjoyed it, please give us a like and subscribe to our channel for more videos like that. Next topic will be terraforming Mars and Moon, and what potential technologies we can apply for it, as well as what technologies we can develop in order to facilitate it. And by that I mean developing a fully livable atmosphere and fully livable ecosystem for us humans as well as for animals and for plants, so that we'll be able to create something resembling Earth.
Also, please check out our store. We have a lot of good consumer electronics at really low prices. Thank you and have a great day.